All right, so here we are on exam 3, part 5, and in this part we are going to derive the Crank-Nicholson finite differencing scheme for the heat diffusion equation and show that it has no stability constraints. So we start this off by just jumping right into it. We have our t to the j of n plus 1, and that is set equal to our plane temperature at position j at time n. And that is being added to our r, which is then multiplied by, got a little bit of a string going on here. So we'll have, this is just calling back some of the previous functions. We'll have t to the n j plus 1, and that is being subtracted from 2 of t to just n and j, and that is being added to t of n j minus 1 and really bad 1, and then that is being added to t of n plus 1 to j plus 1, and then finally we are adding t n plus 1 to, instead of j plus 1, j minus 1. And this is all being divided by 2. Well, yeah. Well, so let me just go ahead and chuck another set of parentheses in right there. Alrighty, so now what we are able to do is simplify this up a little bit more. So what we get is we have negative r being multiplied by t of n plus 1 as well as j, terrible j, sorry about that, plus 1, and then this is being added to, we have 1 plus 2r and that is going to be multiplied by t to the n plus 1 of just j, and then that is being subtracted from r times t of n plus 1 of j minus 1. And then that is set equal to, r of t n plus 1, j plus 1, and that is being subtracted from 2 r of just normal tjn, and finally that is being added to t of n j plus j minus 1, not plus 1. Sorry to get the little bit of confusion there. So all that we really did in this step was just separate our TJ or our subscripts from the variables from the n plus 1s in the subscript and the n's. So next step is we're going to replace the superscripts with our e to the ik delta x and then with the t's. We're also going to bring out the t's so that we, or factor out the t's so that they're only on the outside and not on the inside anymore. So that's going to leave us with t of n plus 1 j, and then that is going to be multiplied by negative r e to our ik delta x, which is what I mentioned we were bringing in, And then that is going, let me just redo that a little bit. Okay, sorry about that little interruption. My roommate just came home and he was seeing who was here, and I don't have a live sign like on air, so didn't know I was recording. So let's just pick up where we started off. So we have our negative r e to the ik delta x, and that is going to be added to 1 plus 2r and then lastly going to be subtracted from re, because remember in this step we are bringing in the e to the ik delta x. Oh, sorry, brain fart. Okay, and then that is going to be set equal to t and j, because remember, factored that out, and the ones that we didn't, we just replaced. And then it's going to be equal to not negative re to the ik delta x, but just, oh, geez, re to the ik delta x. And then that's also going to be added to our 1 plus 2r. And then it is going to be plus re instead of negative like we had in our last expression. So we've got our re, I, k, delta x. All right, so now we can simplify this up even a little bit more by bringing back cosines that we did, and I think it was part, I think it was just the last, part 4. So this expression is definitely going to change a little bit. So now we, alongside adding in or factoring or replacing certain things with the cosine, we are also simplifying it just a teeny bit more. So we have our tn plus 1 j, and then that is going to be set equal to just a regular t and j. And then, all right, good line there. We are going to have 2r cosine of k delta x. So that stays the same, just like the last part. And this is going to be added to r 1 minus 2r. Well, I guess not r minus, because in these cases it was, oh, you know what? Made a little error right here. This is subtraction. That's not supposed to be addition. So yeah, r1 minus 2r. And then on the bottom, we are going to have 1 plus 2r, this one right here. Catching little errors, I'm glad I did. And then that is going to be subtracted from 2r cosine of k delta, change in position, delta x. All right, now we can simplify even a little bit more. Now that we have our cosines in, we can simplify this a little bit just by moving things. Oh, that's a terrible parenthesis. Just by moving things around. So now we will get our Tn of j stays there. That doesn't go anywhere. Can't really do anything with that currently. And we still have our division. But now our 1 minus 2r is being multiplied by 1 minus the cosine of k delta x really bad x. And then on the bottom, it is literally the same thing except for an addition, sticking along with what we had over on the left-hand side. But this still stays negative. This does not become addition. Well, I guess subtraction, not negative. You know what? And because we have 1 minus cosine instead of 1 plus or something else, we know that it will be greater than 0, which is what we are looking for. All right, so now that we have this expression, we can go ahead and get rid of the cosines and instead use y. It'll just make it a little simpler for when we are at the end of our step. So this now equals, after we do our substitution, we, TJN, our guy, stays with us through almost all these parts, but now it becomes inside. We have 1 minus 2ry. And then on the bottom, we have 1 plus 2r, terrible plus, 2ry. And we also know that in this case, our y needs to be greater than 0 alongside our r, just to make everything good and working properly. So now we can shrink it down a little bit more by using 2. So, I'm sorry, not 2, by using z. We can turn 2ry into z, just add, so like creating a new variable here. Go ahead and just signify or show that just so we know that's a 2 and that's a z, so that we don't get mixed up, because the handwriting can be a little sloppy with this program, which I do apologize for. I just, moving into a new house, lost the whiteboard in the move, which stinks because I literally got it just for this final video, because I hadn't had one in previous videos, as you probably know from watching them. So then we have our n. Oh, excuse me. In this case, we have r now. And then we have j. Actually, no, it's still n. I don't know what I'm talking about. And then it is being multiplied by 1 minus z over 1 plus z. And now, just because the r and the y were in here, obviously, because they were part of our z, we have to make sure, or the parameter is still set that it is above 0. So now we can infer that 1 minus c over 1 plus c is always less than 1, which means that our delta x will be constantly increasing, going to infinity, so that the accuracy will, and then it shows that the accuracy will decrease, but it will remain stable due to our bounds. So honestly, we just simplify it a teeny bit more, get 1 minus z over 1 plus z, like I said, is greater than 1. So this, just like I said earlier, helps us stay in our bounds. So this is the end of part 5, and I will see you in part 6 for coding.